Well, thank you so much. I cannot tell you how thrilled I am to be here with you tonight in this magical place, really. And you are all so beautiful. I wish you could see yourselves from where I am. Thank you so much for coming. And well, what can I tell you? I think basketball, what a performance, by the way. Let's give another round of applause. Speaking about a tough act to follow, and I feel like they have already expressed everything you need to know about infinity. So, but in a non-verbal, musical, artistic way. So let's try to say something about it as well. What is infinity and is it real? Well, let's see. At first glance, everything around us is finite. The number of minutes in a year or in a lifetime. Even the number of all grains of sand on all beaches on Earth. I just came from Ibiza, so it's kind of on my mind, the sand. Even the number of all atoms in the observable universe. I mean, universe is 14.7 billion years old, give or take. So multiply that by the speed of light, and you get sort of a big sphere that all the stuff in there is what we can observe. It's a huge number of atoms, but it's still finite. Is human experience inherently limited, or is there something in our lives that defies the confines of the finite? Is there such a thing as infinite? And if it is, how do we find it? Can mathematics tell us something about this question? Well, let's find out. Before I jump into math, I want to quote our dear friend Carl Jung, who said that the decisive question for a human is he related to something infinite or not? That is a telling question of one's life. Only if we know that the thing which truly matters is the infinite can we avoid fixing our interest upon futilities and all kinds of things that don't have real importance. If we understand and feel that right here, in this life, we already have a link with the infinite. Desires and attitudes change. Speaking about infinity in mathematics, we first have to make a distinction between two different types of infinity: potential infinity and actual infinity. Potential infinity is the idea that if you consider the sequence of natural numbers, 1, 2, 3, 4, 5, and so on, it's not going to terminate. It's going to continue forever. We can always add 1 to every number, right? Think of a big number, a billion. Well, it's big, but billion plus 1, billion and 1 is still bigger. Billion and 2 is still bigger, and so on. In other words, the process does not exhaust itself. However, at every moment, we only conceive of finitely many numbers. The process cannot be completed. And so, this is sort of like infinity light. It's like a cocktail without alcohol. Cocktails are amazing, aren't they? And so, but that's how philosophers initially thought about this. In fact, Aristotle, in the 4th century BC, denied the existence of actual infinity. That is to say, the existence of the entire sequence of natural numbers. And said that we can only allow ourselves to consider at every moment just a finite collection. Yes, you can add 1, and you can add 1 more, and add 1 more, but at every moment you are confined by the finite. Now, actual infinity is a totally different thing. It means that we accept the existence of the entire collection of natural numbers. That we accept that it exists as an object in and of itself. What mathematicians call a set. We call it n. for natural numbers. 1, 2, 3, 4, dot, 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 because obviously I cannot list them all. There are infinitely many. The set is infinite in the sense that you cannot set up a one-to-one correspondence between it and any finite set. There will always be more elements, you see. A finite set is a set, for instance, the set of all of you in this auditorium. You cannot set up a one-to-one correspondence between the set and the set of natural numbers, because I've been told there are about 750 of you. Well, but 751 is not included in this set, but is included in the set of natural numbers. The set of natural numbers is bigger than any finite set. It is in this sense that it is infinite. The idea of talking about infinity in these terms, in terms of what mathematicians call sets, came from a great German mathematician, Georg Cantor. And he gave a beautiful definition. A set is a many that allows itself to be thought of as one. A set is a many that allows itself to be thought of as one. It's a kind of intuitive definition. It's one of those things where mathematicians actually have to take something on faith. It's a kind of a dirty secret that I'm not supposed to disclose here. But in mathematics also there are certain concepts which cannot be defined. They're kind of primordial concepts, which appeal to our intuition. And this set, notion of a set, is one of them. So now, let's accept actual infinity. Let's accept that this set exists. Immediately, we run into a bunch of paradoxes. For instance, inside the set of all natural numbers, you have the set of even numbers. Yeah, there is a set of even numbers, but there is no laser point, so that's fine. You can have one, but not the other. So maybe I press some button. I have to press some button. Anyway, I guess you can see it anyway. So 2, 4, 6, 8, and so on. Clearly, it's a smaller set because it excludes all odd numbers. However, an interesting thing happens. You can set up a one-to-one correspondence between even numbers and all numbers. You see? Here's how we do it. We assign, so on the left, you have the set of natural numbers. On the right, you have the set of even numbers. But I can assign to every number an even number and vice versa, so that to each number, natural number will be assigned a single even number, right? So to 1, I assign 2, to 2, 4, to 3, 6, and so on. To every number n, I assign 2 times n. So to every natural number, I assign an even number, and this way, they get paired up. That's what we mean by one-to-one correspondence. So you see, you have something which is smaller at first glance. It's kind of half the size, because they're even numbers, but you exclude the odd numbers. And yet, it is of the same size, actually, because you can set up a one-to-one correspondence. Nothing like this can happen if you talk about finite sets. If you have a set of 5 elements and you have a set of 3 elements, you cannot set up a one-to-one correspondence. But here you have 2 infinite sets. One is inside the other, and clearly smaller, and yet they are in one-to-one correspondence. So this suggests that maybe every infinite set, is in one-to-one correspondence with natural numbers. Not so fast. Actually, Cantor's beautiful contribution is the so-called diagonal method, by which he showed that infinity comes in different sizes. You see? So it's not enough that it's already mind-boggling that you accept the existence of this actual infinity. But it turns out that this is just sort of the opening statement of a beautiful theory. There are infinitely many infinities as well. And I'm going to just very quickly go over it. You can consider a set of binary sequences. Binary, it makes sense because you know that every computer program ultimately gets transcribed into a sequence of zeros and ones. But here we consider infinite sequences of zeros and ones. Mind you, computer programs are always finite. just like everything that we observe, like atoms and grains of sand. But here, we make a leap of faith, just as we did when we talked about the set of natural numbers. And we say, let's look at all possible sequences of zeros and ones, which are infinite. So here's one of them. 0, 1, 1, 0, 1, 0, 0. Collection, consider collection of all of them, all of those sequences, they're infinitely many, obviously. Is there a one-to-one correspondence between them and the set of natural numbers? In other words, can you label all sequences, enumerate them by natural numbers, or are there more sequences than natural numbers? You see? So the question before us is whether we can assign a number, we can label every sequence of that nature by a natural number in such a way that every sequence gets labeled by a single number and vice versa. So let's try. For example, let's say that the first one will be all zeros. The second one will be all ones, and so on, okay? So let's suppose we can compile a list where we enumerate all possible binary sequences. Then Kant, the genius of Cantor was to show that that's not possible. And here's how he argued. He said, let's look at the diagonal. You see, the diagonal is marked in red. So you take the first digit of the first sequence, the second digit of the second sequence, and so on. So you get 0, 1, 0, 0, 0, 1, 0, 1, etc. And then switch them. Switch from red to blue. So the first one was 0, but you put 1. The second one was 1, you put 0, and so on. So you get this blue sequence out of the diagonal, but it is not the diagonal. It's the opposite of the diagonal, you see? How clever. And now I claim that this new sequence is nowhere to be found on this list for an obvious reason. Because it cannot be S1, because it differs from S1 in the first digit. You see, for S1, the first digit is 0. For S, it's 1. It's different from S2 because it has a different second digit. It's different from Sn because the nth digit is different from the, it's the opposite from the nth digit of Sn. So this sequence is not on our list, and our list is incomplete. It is not possible to enumerate all sequences, binary sequences, and therefore the collection of those binary sequences comprises a set which is bigger, strictly bigger than the set of natural numbers. You see? Infinity comes in different sizes. Did you know that? Well, some of you probably did. And you can continue this because we started out with natural numbers. We came up with binary sequences. In fact, there is a canonical procedure which enables you to construct more and more sets of that nature. I'm not going to get into details. And each time, you get a bigger set. Now, bigger is kind of a loose notion. In mathematics, we call it cardinality. A finite set, a cardinality of a finite set is just a number of elements. And two infinite sets are called a set to be of the same cardinality if you can set up a one-to-one correspondence between them. So obviously, the cardinality of the set of binary sequences is larger than the cardinality of natural numbers. And this way, we get an infinite hierarchy of infinite sets, larger and larger cardinalities. That's what happens if you accept the existence of an infinite set. If you accept the fact that 1, 2, 3, 4, 5, going all the way to infinity, exists as a whole entire collection, and not just the first few of them, your universe expands, your mathematical universe expands. But you see, in mathematics, we try to organize things. After all, it's the most cerebral and the most logical subject. So, how do we go about it? We start with a system of axioms. And then we derive various statements, which we call theorems or lemmas, propositions, and so on, from those axioms by using the standard rules of logical inference. The most commonly used system of axioms in set theory is called Z of C. Z and F for two names, one of which sounds very close to mine. No connection, as far as I know. Zermelo and Frenkel, and C stands for the axiom of choice. Guess what? One of the axioms of ZFC is the axiom of infinity. In other words, the founding fathers of the subject knew that you cannot derive the existence of actual infinity from anything. It has to be taken as an axiom or not. That's your choice. People outside of mathematics, I think for people outside of mathematics, it might come as a surprise because the way mathematics is usually presented is that it's like everything is set in stone. It's always been the same. But in fact, there is a heated debate, has been raging for over 100 years, as to which system of axioms we should choose. And a priori, there is no reason to choose one over another. So the most cerebral subject of all is still human activity. And as a human activity, it requires a choice. Do we include the axiom of infinity, which basically states that the set of natural numbers exists, or not? Interestingly enough, it has been proved that this axiom is independent from the rest of the axioms of ZFC. So we have no help, because it could be that you say, okay, well, maybe we don't have to adjoin this axiom. Maybe other axioms of ZFC will somehow imply it. No, we know it won't. Nor would they imply its negation. It really is our choice to include it or not to include it, or we could even include its negation and actually say an infinite set does not exist, as some do. If we do that, if we remove the axiom of infinity, we get a new system of axioms. In principle, it's a bona fide, just as bona fide system as ZFC. And we have arrived at what's called mathematical finitism, which is an attempt to develop mathematics operating strictly with finite sets and potential infinity, but refusing to accept the existence of the actual infinity. So I have a confession to make. I have always dismissed the mathematical finitism up until now. I kind of look down. It's like, how can you not accept infinity? It's so beautiful, you know? But then I thought about it. Actually, as I was preparing for this lecture, I thought about it, and a friend of mine actually told me about this movement in France, in literature, called Oulipo, Ouvroir de littérature potentielle. It's nice, potentielle, it's like potential again, right? It's an experimental literature workshop in France, and actually it became more prominent since last year when its president got a prestigious Goncourt Prize. The idea is to create literary works subjected to various formal constraints. For instance, a famous novel, The Disappearance, is a 300-page novel in which there is not a single time mentioned the letter E. Okay? Wow. Wow. So it's a form of art, you see? And that's how I came to appreciate finitism. I feel that these mathematicians decide to work under some self-imposed limitations and see how far they can get, right? So it's not a bad thing, as long as they remember that they imposed those limitations. The problem is that mathematics that they develop under this constraint of not accepting actual infinity is limited, it's more limited and impoverished. Not only can they not prove anything about infinite sets, well, obviously they don't accept them anyway, so fine. They can't even prove some results about finite sets, which we, infinitists, can prove for them. Moreover, actually Georg Cantor, the father of set theory, he made an interesting observation. He basically said that by negating actual infinity, they are tacitly, secretly accepting it. Because from where would they be drawing those numbers if that infinite set did not exist? You see? Because they say, oh, we accept a finite set from 1 to n, and we can always add 1 to it, but we don't accept the whole thing. But where are you going to take them from if that set does not exist? It has a borrowed reality, as Cantor said. You know, the analogy I feel is like a bitter lover. I don't need your infinity. You know, I can do without it. Watch me. Which is, you know, is a worthwhile pursuit. But again, as long as they remember who started it. So most mathematicians today do accept axiom infinity, simply because it leads to a richer, more diverse, and more elegant mathematical universe. You see, it's not based on any dogma or ideology or religion or mysticism. It's a purely pragmatic choice. We would like to develop a more fruitful and interesting theory, something fun to play with, and clearly accepting actual infinity leads to such a theory. As David Hilbert, one of the defenders of a German mathematician who at the beginning of the 20th century was one of the major defenders of Cantor's theory. And by the way, I want to say there was a heated debate and there was a lot of sacrifice by Cantor personally and others, because he was criticized very harshly at the time. His works in which he introduced the notion of infinite set and his diagonal method and so on was at the end of 19th century. And the debate raged for years. Some, like a great French mathematician, Henri Poincaré, talked about Cantor's theory as a pathology on the body of mathematics. Luckily, there were others like Hilbert who said, no one shall expel us from the paradise that Cantor has created. You see. Today, we accept, it's more than that, because I would say, as a practicing mathematician, every textbook you open, every textbook in mathematics, be it a theory of differentiable manifolds or vector spaces, it starts with a definition. What is a manifold? What is a vector space? What is a group? It always says a group is a set endowed with some additional properties satisfying such and such axioms. But every object is introduced first and foremost as a set. We cannot even imagine in the 21st century, we cannot imagine developing mathematics without using Cantor's ideas. But they were hard won, and we have to remember that. Still, wouldn't it be nice to have a formal proof that infinity exists? So I would come in front of you and say, look, here it is, and show it to you. In this regard, a useful analogy, for me at least, from an unlikely source. D.T. Suzuki was a great scholar of Zen Buddhism. He has written some scholarly works, but also nice popular books about the subject to introduce Western audience to it. He talked about the distinction between two concepts in Buddhism, Vidyana and Pragma. Now, I went down the rabbit hole of finding out how precisely to pronounce it. Nobody knows. It's an old Sanskrit word, and there are different schools of pronunciation. So my pronunciation is approximate. Vignana and Pragma. Okay, let's just call it that. Vignana refers to analytic knowledge, dissecting, describing, discriminating, evaluating, accumulating, which is more or less our education system. So every day kids go to school and they're given more and more and more. Just like numbers. Prajna is a totally different thing. It's an intuitive understanding. When you go, aha, I got it. You're not evaluating. You're not dissecting. You're not describing. You just get it. It's an intuitive understanding. It's an insight, grasping reality in its totality, as it were. And in this regard, Suzuki made an interesting comment which is relevant to this conversation. He says, Vignana, which is this analytic knowledge, can never reach infinity. when we write the numbers 1, 2, 3, and so on, with what I started with, we never come to an end because it goes to infinity. By adding together all those individual numbers, we try to reach the total of all numbers. But because they are endless, this totality can never be reached in this way. That's potential infinity. Prajna, on the other hand, in 2 is the whole totality. Instead of moving through it step by step, 1, 2, 3, and so on, it grasps it as a whole. It does not appeal to discrimination. It grasps it from inside, as it were. And then he explains, the moment grasped by prajna intuition is satori, what Buddhists call awakening or self-realization. So, if we grasp actual infinity tonight, we will have reached satori. Why not? With beautiful music, cocktails, the magical concert hall. I think we can. But as soon as you have said, I caught it, it flies away. It's no longer there. It's not something you can show to somebody else and say, here it is, I got it, because it evaporates. And so it is with infinity, I feel. It's not something, I wish I could bring it with me. I would need an infinite suitcase, I guess. My suitcases are finite. We can't show it to others, but we can feel it from inside. That's in our lives. But in mathematics we have a trick. We can take it as an axiom. You see? We can take it as an axiom. Nobody can prevent us from doing so. And see what happens. And see what a fruitful and beautiful and rich theory comes out of it. And that's pretty much the development of mathematics of the last 100 years, since infinity became widely accepted. Of course, I have to mention here a great man of Copenhagen, Niels Bohr. By the way, you know, when I was a kid, I had his photograph on my desk. He was my hero. I read his biographies, and I always felt some sort of affinity with this man. So it's kind of interesting because I feel like finally I make a homage to his, place of birth and place where he worked and made his amazing contributions to humanity. But, I always felt that, some kids would have pictures of rock stars or actors. I had Niels Bohr, and I'm proud of it. How wonderful that we have met a paradox, right? We have met a paradox here tonight. We have met several, actually. Now we can have hope of making progress. He was kind of like a Buddhist monk, to me. And his the kind of things he said, they sound like Buddhist koans. And he came up with, he codified it, specifically in connection with the interpretation of quantum mechanics, which is a daunting task, as you probably know, and probably many of you have attended previous Science and Cocktails talks on this subject. Bohr seemed to be a wiser and deeper thinker than others. And he could see that our traditional approach, what do I mean by it? Traditional approach, I mean that we want answers. And we want answers now. We want definitive answer. It is this, or it is that. Case closed, you see. That I feel like we put so much premium in our Western society today on answers. Specific answers, like that or it's like that. But Bohr saw in quantum mechanics that that is not possible. That actually there are complementary points of view. And from one point of view, you get something which is kind of opposite to what you get from the other point of view. For instance, is an electron a particle or a wave? Well, guess what? It depends on how we set up the experiment. or how we ask the question. You probably know about the double slit experiment. I imagine many of you have attended previous talks or have seen it elsewhere. You put two slits, you take a wall with two slits, and you start throwing electrons at it, and then you put a screen behind. If the electrons were little pellets, on the screen, you would see two bumps behind the two slits. But that's not what we are seeing. We are seeing an interference pattern, as if an electron interferes with itself, as if each electron goes through both slits at once. Then we say, well, we're going to catch the electron. I'm going to put a detector behind one of the slits to see whether it went through this one or through that one. So we change the experiment. We change the way we ask the question. And as a result, the electron starts behaving differently. We start seeing the two lumps as if they were particles. So if we did not put a detector behind the slit, an electron would behave as a wave. But if we do, it would behave as a particle. And then you can complicate this by erasing the information, and so on. And an electron, like a well-trained actor, is always going to do the right thing. It's like with a weary smile, you know. It's like, oh, now you want me to do this? Okay, fine. So you see, it's neither and both. And Niels Bohr codified it in the complementarity principle by saying that some properties of quantum systems are complementary to each other. And if you measure one of them, you will not be able to measure the other. Or if one of them is exposed, then the other one won't be. Which brings to mind a quote from Werner Heisenberg, who was his sort of brother in arms in the Copenhagener interpretation, which, by the way, I think is misunderstood by a lot of people. I think it's much deeper than a lot of people think. But Heisenberg said, what we observe is not nature itself, but nature exposed to our way of questioning it, you see. That's the essence of complementarity. Can you imagine the kind of revolution that these guys created at the beginning of the 20th century? More or less around the same time that the heated wars over set theory and infinity were raging in mathematics. Bohr wrote, we must be clear that when it comes to atoms, language can be used only as in poetry. In other words, our traditional know-it-all, answers approach doesn't work. In poetry, you don't look for answers. You communicate something else. And interestingly enough, modern science, physics, mathematics, biology, one could say, is becoming more closer to poetry than to this naive, some people say, I believe in rational thinking, only facts. And yet they believe in something, right? They believe in rational thinking, so which is itself an irrational belief. But nobody told them, so it's fine. You see, for such people, poetry is bad, it's a swear word. But the greatest ones, Niels Bohr, Heisenberg, they understood. And in fact, here's an example. A physicist is just an atom's way of looking at itself. That's Niels Bohr, huh? Wow. I wish I could meet him, honestly. And another quote from Bohr. You can recognize a small truth because its opposite is a falsehood, but the opposite of a great truth is another truth. Like in the complementarity principle. No, you're not thinking, you're just being logical. Well, after a few cocktails, it resonates more, right? I mean, everybody can be logical, let me tell you, as a mathematician. But try to be poetic, that's a higher task. But still staying within the realm of reason, And this is another one I love. There's some things that's so serious that you have to laugh about them. That's Niels Bohr. There are a bunch of other quotes I wanted to put, but my time is limited, it's finite, unfortunately. So, which, by the way, I wanted to mention this earlier, and I forgot, but I want to say it now. So there is an important distinction you have to make. We are not talking here about infinity of the physical universe. You see, we have 3 dimensions of space and 1 dimension of time, right, in our physical universe. And of course, it's a very valid and very fascinating question as to whether the universe is infinite in space or in time. Whether, for instance, the universe will continue on indefinitely, or there will be a big crunch and it will collapse until a point the way it started from the Big Bang. And we don't know. Physicists don't know. There are different models. But the jury's out at the moment. We don't know. Likewise with space. All we know is that the observable universe is finite simply because the speed of light is finite and the age of the universe is finite, like I said earlier. So these are all very interesting questions, but we don't know the answers. However, the point I was making earlier about infinity, potential infinity, actual infinity, and so on, the whole discussion, is not about the physical universe. It's about the mathematical universe. It's something that is in our minds, you see. In other words, the physical universe may well be finite for all we know, but we may still be able to accept the actual infinity when we do mathematics, right? Also, there could be infinitely many universes. That's another possibility, which I'm sure some people have talked before me in this series. So, the question of whether or not we accept actual infinity is a question in our minds. It's a question about our us, really. That's what I'm trying to say. It's not about things around us, whether it's possible to go beyond the finite. How do we choose the answer? What resonates with us? You see? That's the paradox, because on the one hand, everything seems to be finite. On the other hand, we get this beautiful theory in mathematics by accepting the notion of actual infinity. And, in fact, questions can be raised as to whether we can even speak about potential infinity without secretly accepting the existence of the actual infinity. You see? To which Niels Bohr said, "You must come to Copenhagen to work with us. We like people who actually perform thought experiments." Which is what we have been doing here, right? So I feel at home, you know? And I think I feel like I came to the right place to be with you and to discuss all of this and to discuss all the paradoxes. I can't imagine a better place. And actually, here is another Great Dane. Let's see if I can say it. My taxi driver was teaching me how to pronounce his name on my way here. Which, by the way, it also speaks something about your city. If even the conversation with the taxi driver is a very deep one, you know? Because he was taking me here and he said, "Oh, there's a beautiful concert hall, and have you been here before?" And I said, "No." And he said, "Oh, you will love it." And I said, "Yeah, I'm performing tonight." And he said, "Oh, are you going to sing?" Don't encourage me. I said, "No, I'm going to speak about mathematics." He stopped the car. About what? So then I told him about infinity and so on. And he said, "How do you pronounce the name of this great philosopher?" He said, "Soren Kierkegaard." Woo! A thinker without a paradox is like a lover without passion. A paltry mediocrity. Is this really how you guys think? Great, I love it. Maybe I move to Copenhagen, you know? The supreme paradox of all thought is an attempt to discover something that thought itself cannot think, you see? This passion is present in all thinking of the individual. Insofar as in thinking, he participates in something transcending himself. I feel like this is what we have been doing together, you know? Trying to think about infinity and paradoxes. And in the end, kind of transcending it, transcending this thought. And here it is. The many has become one. Thank you.
Thank you so much, Professor Edward, for an amazing talk. We have few minutes left for some questions from the crowd. And we will start with, do you think it's possible to prove that actual infinity exists?
So, I don't think so. I don't think we can prove it in the traditional sense of exhibiting it as an object. Because every time I try to do it, I'm going to use a finite description of it. And because it is inherently finite, it's not going to capture the infinity. But it's not something unusual. We are familiar with it in the following sense. Sometimes you read a poem and you feel that you connect to something much bigger than the actual text. So the text appears as a sort of a wrapper for what? For some feeling, for some emotion, for some infinity, one might say. Likewise with music, with art, with works of art. So it's not surprising that in mathematics also we can create infinity with one sort of stroke of a pen by simply including this axiom of infinity. So the axiom of infinity is finite, is a finite text, but its meaning is infinite. So in that sense, we can evoke, I would say it's not produce it, not demonstrate, but evoke, So it's like a finger pointing to the moon, to borrow a famous Buddhist analogy. Don't look at the finger, look at the moon, you see. So likewise, feel it in the essence of what is in front of you. So in the traditional sense, I believe you can't as an object. But we try, and this is art. Creativity, to me, creativity in art is about evoking infinity. It's like, I was listening to basketball earlier, and I felt it, and but I can't display it. I can show it to you. So,
yeah. Let's move to question number 2. If the universe is infinite, how can it expand since infinity does not increase by being multiplied by any number?
No, but that we can explain. So imagine that it can be infinite but still expanding, right? So for instance, the universe is three-dimensional in spatial dimensions, and there's one time dimension. But let's forget about time, and let's reduce it to 2 dimensions. Let's suppose that the floor of this stage is the universe, okay? And so imagine that it extends all the way to infinity in all directions. Now, we can still magnify, we can still kind of blow it up. But we can imagine a movement where every point, let's say, is moving, let's say we call this a center. It's moving away from the center. And so it stays infinite as a totality of points, but each individual point moves. So in this way, it is expanding while still remaining infinite. And that's one of the models of the expansion in Einstein's relativity theory. It could also be like a balloon, which is finite, but you blow it and it grows.
I think we have maybe more time for a couple of questions.
Okay.
So, are paradoxes not meant to be broken?
A paradox is not meant to be broken. I love this. It's like your vows are not meant to be broken, right? But paradoxes. I think, one part of me likes paradoxes. Another part of me wants to break them also, So it's like two natural impulses of, nothing wrong, with either. I think it's like, how to say, it's like yin and yang, it's like finite, infinite. In some sense, they're complementary to each other. And in a sense, we can appreciate both and use both when it is appropriate. So it's like left brain and right brain, like knowledge and imagination, yin and yang, Dionysus and Apollo, and sun and moon, all this love and math, Thank you. You guys have been amazing. I love you.